Hi, my name is Brandon Wolfson, and I appreciate you taking the time to give me an opportunity to tell you about Technology Service Corporation, or TSC, and the technology that we call LIFS today. And we'll go through a couple of slides that hopefully give you a better idea of what LIFS is, how it can be used, and hopefully instill in you some questions about LIFS where you can email me. My email address provided in these slides. And please, if you have questions, reach out to me, and would love to catch up with you to hear what types of position navigation and timing areas where LIFS may be applicable. One of the first things I'd like to do is talk to you a little bit about TSC, who we are, what we do, and what we specialize in. But first, I want to talk to you about Dr. Peter Swerling. So in the 1950s, Dr. Peter Swerling was known for studying different aspects of radar performance. One of those things was the fluctuations of radar return signals from different types of objects, from different types of angles, and those became famously known as the swirling radar models that are still used today and still taught in radar textbooks. After that, Dr. Peter Swerling went on to found Technology Service Corporation, or TSC, in 1966. And the company was founded on the basis of providing subject matter expertise in RF sensors. And to this day, we still provide that same subject matter expertise, although we, as you can see, and we'll discuss here in a moment, we have expanded beyond just radar and in applying those capabilities in a variety of areas that are useful for the Department of Defense and our warfighters to give them a tactical advantage. One of the things that we utilize the RF sensors for today, obviously, is position application timing, which is what we want to talk about LIFS. So TSC, one of the things that I'm proud of and one of the things that we specialize in is in our ability to not just have and retain internal the subject matter expertise on a lot of these technologies and how to apply that expertise to real world applications, but also we've developed a core competency of creating the prototype hardware and now actually transitioning that hardware into full rate production for fielded platforms. We also have several areas of the company that specialize in different types of technologies. So the 6 areas we have shown here: precision weapons, airborne sensors, radar and fire control, electronic warfare, air missile defense, and space systems are the primary areas in which TSC leverages its capabilities to support our defense priorities. Obviously, the LIFS solution will fall into the airborne sensors category. The next thing I wanted to talk about is, why did we develop LIFS? Well, one of the things that we noticed was continued requirements on how to provide precision, position, navigation, and timing, or P&T, in environments where either GPS was denied or in anti-access area denial environments. So, given our background in RF sensing, of course, we naturally lean toward how do we design an RF sensor to solve this problem? Well, the end goal that we had was a couple of different areas. And one of the main areas that we'll talk about today is how do you leverage LIFS to provide autonomous landing of various types of airborne platforms in austere environments onto a ship or into land areas, or maybe we just use it to identify different types of payloads that we want to drop off or pick up. Either way, LIFS, which stands for Location, Identification, and Flight Tracking System, is a valid solution that we can use and that doesn't require GPS. It can work at long ranges, as well as it can operate in covert or low probability of intercept modes, so to avoid enemy detection. Currently, we're experimenting with LIFS to support the Navy Air Warfare Center for their Sailors program, which is sea-based automated landing and recovery. In this particular application, we are applying the LIFS capability to provide flight guidance from a manned or unmanned platform to a ship deck for automated landing. Continue from the left side. Now we'll talk a little more specific about how does LIFS work in the specific CONOP of landing an airborne platform on a ship. Well, first let me talk about what LIFS is. So LIFS is comprised of two elements. So you have the sensor that is mounted on the aircraft, usually downward facing, and you also have tags. The tags, in this case, are placed on the ship deck. Usually multiple tags are placed for additional measurement accuracy and precision. And it could be 3 tags placed in the triangular shape. It could be 4 tags placed in different locations on the ship deck. Either way, as long as they're spaced out far enough that they're used as fiducials. The lift sensor will send out waveforms that will turn on the tags. The tags don't perform any function unless they're commanded to prevent any kind of inadvertent detection. So lifts will send down a signal to turn on the tags, put them in a measurement mode so that lifts can then start making measurements, range and bearing measurements to the actual tags. And the fact that there's several of them spaced out allows lifts to start doing triangulation and trilateralization and position determination relative to those tags. And that's how, at a high level, then lifts will provide that information, the range and bearing and positional information to the aircraft that will enable the aircraft to know exactly where the ship deck is and the orientation of the ship deck. So in this way, the lift sensor then provides the necessary PNT to the aircraft to enable it to do automated landing or simply have situational awareness. The other thing that we get asked about a lot is, okay, well, if LIFS is radiating a signal, how do you prevent yourself from being detected? So LIFS has a software-defined capability in it. So we can develop or utilize proven waveforms that are low probability of intercept and low probability of detection with encryption also for more security. The tags themselves, they do return signals back to LIFS. However, they're only going to return those signals when commanded, and they can also leverage the LPI, LPD, low probability of intercept, low probability of detect waveforms utilized by the system if chosen. Now that we've explored the general concept of operations as lifts for shipborne landing, I want to provide you a little more details about the performance metrics of lifts. So I mentioned before that lifts is comprised of 2 major elements: the lift sensor, which we call the interrogator, usually mounted on the aircraft, and of course the tags placed on the landing area of interest. Well, the benefit of having the tags involved is they're operating as cooperative targets, essentially for the lift sensor. This allows us to use much lower power levels, which has advantages of being a lower probability of intercept, but it also has the advantage that it reduces the amount of power consumption needed by the sensor or the tags. The last thing it does that's probably the biggest advantage is using this RF sensor is not only does the RF energy and RF-based sensing allow us to operate in all weather conditions, whether it's fog, cloudy, rain, dusty, where other sensors may struggle without interference, the RF approach mitigates those problems. And because the tags are involved, we can also extend the range out to a pretty significant order. In this particular case, LIFS is designed to operate out to 10 nautical miles. And we'll talk about the testing here shortly, but we've been able to have great success in validating our LIFS performance. The other thing we'll talk about is LIFS operates at X-band, which is a common band that is used, but also has that good balance of precision as well as range capability. Right now, we're transmitting roughly about 5 watts out of the interrogator, which is relatively low power, and which allows us to keep the total power consumption of lifts to roughly about 75 watts. The size of lifts you can see there in the bottom right hand side, it's roughly about 7.5 inches in diameter, about 4 inches tall, still under 8 pounds. So right now lifts is already a low size, weight, power. However, it provides opportunities as we transition to platforms of interest. There are opportunities for other weight and size reductions based on the need. Lastly, we talked about working out at 10 nautical miles. The accuracy was also very important to us because we wanted something that was comparable or better than GPS. Well, you see lifts, what we've been showing is operating with a measurement accuracy, a positional measurement accuracy of roughly 0.5 meter to 2 meters. And that's dependent on how far away lifts is, the environment it's operating in. But generally speaking, we can achieve the GPS-like accuracy with the lift sensor. So in summary, LIFS is an enabling a technology. Certainly shipborne guidance, airborne landing guidance for shipborne applications is a very practical application for LIFS that's currently underway. And then certainly there's other applications because of LIFS conveniently embedded communications type capability as well, where it could be advantageous. Next, I'd like to talk about the current status. And we've actually made a lot of progress since this slide was created, but we'll go over what the data we have here, as well as talk to you about what we're doing currently with lifts. So we did complete a phase 2.5 back in roughly a year ago, or just under a year ago. And in that phase 2.5, what we did was we took our prototype hardware and we took it out into a real-world application where we flew it on a hexcopter. We've also done some static tests with it. You can see some of the data measurements on the right-hand side of our quadcopter test, and we can see the results that were fairly promising on the range, angle, elevation, and azimuth angle measurements to 3 different tags. So this gave us the confidence that the LIFS concept was going to be a viable option for doing P&T measurements. Now, since then, we've actually completed some tests here in February of 2022, where we mounted LIFS sensor on a Cessna 206, and we took it out over open waters. We had 3 tags placed on the shoreline, and we flew out to several nautical miles while still taking measurement data. Again, making range, azimuth, and elevation measurements to all 3 tags simultaneously, and recording the data and comparing the truth, where we had very positive results. Therefore, again, verifying the range performance of LIFS as well as its operational feasibility over open water, simulating a real-world environment on a fixed-wing aircraft. So we've already touched on a lot of the features of LIFS, but it's probably good for us to kind of just review at a high level what are those key features, advantages, benefits. So, as I mentioned before, because it's an RF system, it has the advantage of operating in all weather conditions. This is important as in some cases cloud, rain, and other things from austere environments such as dust, foliage, other things that can prevent visual, other types of measurement solutions are overcome or mitigated by using the LIFS RF type solution. The other thing is that it's multimodal. So I mentioned there's a software-defined back end to LIFS and as the tags as well. So we can operate in radar-like modes. We can actually use it to also perform communications type technologies. What does that mean? As I mentioned before, the system actually acts like a full duplex communication system, although using radar waveforms. That means is we can transmit and receive at the same time, so the lift sensor can be sending messages down to the tags. The tags can have stored data on them, and lifts can request that data back. That could be ship identification data, it could be payload data, it could be information about the landing area. Whatever it is, we can customize the messaging that is stored on the tags and communicated back from the tags. As I mentioned before, also LIFS architecture is low size, weight, and power, or SWAP. We did this to make sure that we can integrate it on a variety of types of aircraft, including UAS. We can put it on smaller UAS at 75 watts and under 10 pounds. It's suitable for some maybe Group 3 UAVs, certainly for Group 4, any manner of large fixed-wing or motor aircraft. The other thing that is great about LIFS, is there's applications beyond just what we described in terms of using navigation aid and landing aids for the sailors application that we're currently applying it toward. As I mentioned before, since the LIFS tags can store different types of data, you could use this for payload drop-off and retrieval. You could simply put a tag on a payload. LIFS can provide guidance to that payload, go to the right one that has the right ID or other types of characteristics that the operator has been told to look for. Lastly, the LIFS integrated communication link provides secure data link outside of normal communication bands. What does that mean? So I mentioned earlier that LIFS operates as X-band. Well, this provides a alternate way of providing communications. This could be used in, let's say you put tags in a open area and you wanted to set up an ad hoc PNT solution. Then those tags could store different types of not just fiducial data, but also other types of important information on it, so that any aircraft, Blue Force aircraft or vehicle or personnel could come into the area that is equipped with a LIFS sensor. Can be used, then the tags can be used to help set up PNT for that ad hoc stand-up network. And what is enabled by the data link flexibility of the LIFS tags and sensor pair. So that's a summary of the LIFS benefits. Again, GPS is not required because of its unique and novel approach to mixing radar modes with full duplex communications. Provides multi-purpose capability and a second secure data link for C2. It also provides lifecycle savings because we were able to reduce the size, weight, and power and cost due to the cooperative nature of the LIFS paired with the tags. And then lastly, it can be a standalone PNT solution, or it can be integrated with other types of solutions for a fused sensor application where we would take advantages of all the different types of sensors that are out there. And so the modularity and scalability of the system is a very important feature that it also offers. One of the next things we started looking at, since we had positive test results, both static and dynamic, and in a real-world environment flying over open waters on a fixed-wing aircraft, we've been in parallel working with potential transition partners. We identify PMA 263 with the TRUS or TRUAS program as a potential target of opportunity. And just an example, in this case, the Marines could deploy the tags on the ground in a particular area of interest, and the UAS that's equipped with LIFS could just find the tags and land in that designated area. And this reduces manpower needed for landing zones. But of course, it could still be used for guidance and many other applications with UAS. The low swap of LIFS does create that opportunity for it to be scaled to the level required and power required for the UAS applications, including TRUS. So what do we do next? So the transition, there's a few things that we would do. We're continuing to update and optimize the real-time navigation software. So right now we're making lots of range measurements, and so we're converting that into tracking software that could be then converted into actual navigation. And so some of that needs to be honed and wrapped up. Other things that we'd be doing is integrations with the avionics flight control. So in a UAS, that's something we've done in the past, and we would simply take the output of the first task of the navigation software and use the avionics flight control software to be fed by that output of the navigation feed for flight control. And of course, with any kind of platform, there's always some kind of volume or mounting constraints that we need to work within. So part of the transition task would include the update of the physical design to make sure that we could mount it as appropriately required to the particular platform that we put it on. And of course, lastly, once we've worked on the software, worked on the flight controls, got it mounted to the aircraft in an appropriate location, then we want to do a lot of field testing and any kind of incremental refinements from what we learned from that field testing. All in all, we're thinking this is roughly a 12-month development cycle with a follow-on 6 months of testing and refinement at roughly about $3.5 million. We also look at the other types of markets that lifts could be applicable to. So certainly the underlying approach of this radar type combined with communication sensor has a lot of applications that may benefit from it. So it could be used to serve as a secondary PNT source in a battlefield. I alluded to that earlier, as tags could be placed in an austere environment, and certainly could set up our own ad hoc PNT solution with just the tags and lifts on different vehicles, both ground and air. Also, lifts can be used to create long-range C2 for unmanned systems. We're looking a lot at this, where we can leverage radar waveforms and the communication waveforms in a different way than we've described earlier, simply by using other fielded radars that are out there, equip them with lift types waveforms. The tags could be put on the UAS, so essentially operating lifts in the reverse of what we've talked about earlier. But in this case, it was shown on the bottom right-hand side, the lifts waveforms, let's say they're put into a shipborne radar. That radar would then be able to track, theoretically, the outbound UAV. And as that UAV is getting to a point where the traditional C2 is out of range, then the radar waveforms could actually embed in them the command guidance signals that can be received by the tags on the UAS. And we have actually done some modeling and simulation of this, and it looks like a very viable path forward. So whether it's the traditional sense, where the lift sensor is on the ground-based airborne platform with the tags placed in areas of interest to be used as fiducials, or we're simply using lift's waveforms incorporated into other previously fielded radars and tags, the low swap tags, being put on platforms of interest in order that we can track them and send embedded command and control signals in those radar waveforms out to those, in this case, UAVs, as what's depicted, to provide beyond line of sight and extend the range of the guidance. Either way, the lift's capability provides a lot of utility. And commercially, lifts could provide additional enhanced accuracy over GPS, only in systems, precision launch and recovery for mobile delivery systems, and confined situations, where GPS signals may be interrupted, such as canyons and caves. There's other types of PNT needs that are outside of the DoD that we believe this could be applicable to as well. So what is the next phase of this program? Well, obviously, much like a lot of these SBIRs, we're looking to find a transition partner. So what we would like to do is we're offering lifts as a payload product. So this is as we mentioned before, the swap C of lifts should be an enabling form factor, as well as its affordability should make it applicable to several different types of platforms. We're looking to obviously get some RDT&E and NRE to help finish the transition for the particular platform that it gets selected for. And just for a frame of reference, in terms of when I talk about low swap C, target price for lifts is under $100K for the airborne sensor or interrogator, and the tags less than $10K each. And so we've already ordered these prices, we're bottom up, build up, as well as we've developed other products that are similar to lifts complexity and design types that are also in these price ranges. So we've got experience in developing these types of sensors across TSC for many other types of applications, and a lot of familiarity with how to transition these types of technologies and actually have the in-house production and integration capability to do so. So that brings us to the conclusion of the presentation. I really do thank you for your time and for giving the opportunity to present to you TSC and its lifts technology. So in summary, TSC is a employee-owned, small business that we've specialized in the research development of RF systems and assemblies, including the things such as radars, missile electronics, communication systems, and antennas. We've leveraged that capability to, in many cases, transition into production. Our goal is to always provide warfighter value. So LIFS helps enable the optimization, position, navigation, timing, and GPS denied scenarios. Right now, we are leveraging that capability to demonstrating it for ship-based landing of airborne platforms. And it has many other applications that it can be used for that we've discussed, such as providing navigation guidance in just general A2AD environments, GPS denied environments, as well as landing on designated landing areas or providing vert rep or the payload drop off and retrieval. Thank you very much.